Finally, we arrive at deriving and using our fundamental kinematics equations. Now, over the past couple weeks, we've determined that we have kind of our three main quantities of interest here in kinematics, our position, our velocity, and our acceleration. And from a calculus perspective, we can kind of step down this ladder by taking derivatives, or of course, looking at the slope of various graphs. And we can go back up from acceleration to velocity to position by either taking integrals or looking at the area. Now, these are very general relationships that work really well, but there is one particular case that we're going to be using a whole lot in this class, which is the case of constant acceleration. So let's consider, for instance, a cheetah, which you may not be aware that the cheetah is the natural enemy of the turtle. The cheetah is the natural enemy of the turtle. Let's say this cheetah starts off at some velocity v0 and accelerates at a rate of a. So it gets faster and faster. And for the moment, it doesn't really matter whether we're getting faster or slower, but I guess we can assume we're getting faster. And what we'd like to ask is, because we care about Shelley, we want to know where is this turtle at some later time. We'll call this later time delta t. And how fast is this cheetah going so we can avoid it? Well, we're going to take a graphical approach here. Now, some of you probably have seen these equations before, but I still want to derive them for you to show you where they come from. So we're going to sketch here a graph of velocity versus time. Now, I've said that our cheetah starts off at some velocity v0. So here at time 0, we're going to have it start right there, so we'll call that v0. And then we're going to have it increase. It's going to accelerate at a constant rate. We're only concerned about constant acceleration here. So it's going to accelerate at a nice constant rate for some time delta t, and it's going to arrive at a velocity v final. Now, one thing you might ask is, what is that v final? How fast is it going? Well, we can go back to our definition of acceleration as the slope on this graph and remind ourselves that the acceleration then, which is the slope on this graph, has to be the slope of this line, delta v over delta t. Now in this case, this is technically the average acceleration, but of course it's a constant line, so it is also the instantaneous acceleration for this whole time. And what I can do is I can rearrange this a little bit and just multiply the delta t over delta v equals a delta t. And reminding ourselves that delta v here is going to be v final minus v initial. We can arrive at our first kinematics equation that the final velocity of the cheetah will be v0 plus a delta t. That is, the cheetah ends up being a delta t faster than it was before. So that is our first kinematics equation and one of our most important. We'll get 3 today. Our second kinematics equation instead asks, how far do we go? And for that, we need to do a slightly different treatment. And what we actually need to consider is that we're stepping from velocity back up to position. And so we need to consider the area under this curve. Now, you can kind of see that this area consists of kind of two parts. There's a rectangle, A down here, and a triangle, B up here. So we'll take these one at a time. And we'll say that delta x, the distance that our cheetah goes during this time period, will be the area of A plus the area of B. So let's look at the area of A first. Well, you'll notice it's a rectangle, and I can do base times height. Well, it's got a base here of delta t and a height of v0. So I end up with v0 delta t plus, well, in this triangle, okay, I know 1/2 at squared, 1/2, giving away the ghost, 1/2 base times height, excuse me. I'm just going to write this in a slightly different order and do the height first, delta v delta t. Now, for those of you who've taken some physics before and I just blurted it out, you'll notice this 1/2 delta v delta t is not usually the way we write it. So we're actually going to borrow our delta v equals a delta t equation from here, and we're just going to plug that in 1/2 a delta t delta t. And what we find is we get our whole lovely equation. If I rewrite the delta x, if you'll excuse that as x final, and I'll move kind of like we did here, the x initial, x0 plus v0 delta t, plus our good friend 1/2 at squared, a delta t, the quantity, squared. And this is, of course, our second kinematics equation, and one that we'll be using a whole lot this year as well. I like to refer to this as the distance equation, the 1/2 at squared equation. It is a lovely friend to all young physics students. Now, again, to the more experienced among you, you may say, Mr. Bates, you have left out a third important kinematics equation, and you are right. There is a third kinematics equation, which reads v final squared equals v initial squared plus 2a times the displacement of the cheetah, 2a delta x. And you're right, that is an excellent kinematics equation, and we'll use it often in this unit. And I'm not going to derive it for you today. Many physics teachers do derive it for you, and you can, in fact, derive it quite easily from considerations of your other kinematics equations. However, it's not actually at heart a kinematics equation, and so I don't feel right. Deriving it here. We'll derive this one. I'll show this one to you when we get to energy and motion. So this is secretly a kinematics equation. So there are our three equations: the velocity equation, the distance equation, and this last one. And this last one is awfully nice because you'll notice there's no delta t in this one. And I just want to reiterate, these three equations only apply in cases where you have constant acceleration. If your acceleration is constantly changing, then you need to actually do some calculus. If your acceleration changes in kind of a piecewise constant way, if maybe we have an acceleration of 2 meters per second squared, and then an acceleration of 3 meters per second squared, then you can use your kinematics equations, but you'll have to kind of split it up into two parts. Welcome to a worked example for using our kinematics equations. In this example here, we have a Cessna 172 that's on its takeoff roll. We're going to say that it starts at rest, and every time you hear at rest, you should immediately think to yourself, well, that means its initial velocity is 0. It's going to start at rest. It's going to accelerate at a rate of 3 meters per second squared, and it needs to attain a final velocity of 29 meters per second in order to take off. And the question is, how long a runway does it need, right? How much space does it need to actually take off? So in this case, we have a couple different approaches. One thing that's always important, and I realize that I've kind of written it for you here, one thing that's always important is to figure out what you know and what you're going to do with it. So in this case, we happen to know our initial velocity, our acceleration, and our final velocity, and we're looking for a delta x. Now, we also, you might notice, don't have a time period in here, a delta t. And this is one of the places in kinematics where people can get themselves into trouble, because it turns out there's actually two totally viable ways to solve this question. One viable way, maybe the more straightforward way, is to use our first and second equations, our velocity acceleration equation and our distance equation. And what we would do is we would use our first equation to find the time. So in this case, we can say that our final velocity is 29, our initial velocity is nothing, plus 3 delta t, our acceleration times time. Well, we just end up with 29 divided by 3, and we find that in order to get up to 29 meters per second at this acceleration, it takes about 9 2/3 seconds, 9.67 seconds. So this is using equation 1. And then using equation 2, we can just plug in that time and find that x final equals, well, presumably we start at 0. We're not really told. Equation 2, sometimes you can kind of think of it as just delta x. Plus our initial velocity was also nothing. So these first two terms kind of go away, and what we end up with is just 1/2 at squared. You'll often find when things start at rest that 1/2 at squared just gets you where you need to go. So here's our acceleration times 9.67 squared, and you end up with 140 0.17 or so meters. That is, we need 140 meters of runway in order to take off. If it's any shorter than that, we're going to go off the end of the runway. If it's longer than that, that's fine. You'll also notice, though, some of you might say, well, Mr. Bates, couldn't I just use equation 3? And you're right, you could. You could just go straight to equation 3, in which case you would get, you'd plug in your final velocity squared. 29 squared equals 0 squared plus 2 times 3 times delta x, plugging in 3 for a. And if you solve for delta x here directly, you will once again get the exact same number, which is good. You should get the exact same number. And this is one of the great things / the tricky things about kinematics, is that often multiple approaches will yield the same result. And so it's up to you to think carefully about what quantities do I have, what quantities am I looking for, and how can I use the equations that I have to connect those two things. And that's a skill we'll practice more in class.